This is lecture 1.2 of Math 108, Conditionals and Biconditionals. In this video, we will consider propositions that involve the implication and by implication operators. Let P and Q represent unknown propositions. A conditional sentence is a proposition of the form if P then Q. The sentence if P then Q is true exactly when P is false or Q is true. It is false exactly when P is true and Q is false. A biconditional sentence is a proposition of the form P if and only if Q. The sentence P if and only if Q is true exactly when the conditional sentences if P then Q and if Q then P are both true. It is false for all other cases. In the conditional sentence if P then Q, the proposition P is called the sufficient condition or the antecedent. The proposition Q is called the necessary condition or the consequent. It is important that you remember the terms necessary and sufficient as these are frequently used in math. Again, in the conditional sentence if P then Q, P is the sufficient condition and Q is the necessary condition. To understand why these terms are used, we look at the truth table. By its definition, the statement if P then Q is false exactly when P is true and Q is false, and is true for all other cases. This is the truth table of the conditional sentence if P then Q. To understand why these are its truth values, interpret the statement if P then Q as a rule that prescribes a specific outcome whenever condition P is true. This outcome is that condition Q is also true. The statement is true whenever the rule is followed and is false whenever the rule is broken. Let us consider each possible case. Suppose that both P and Q are true. In this case, the rule is clearly followed. So the statement if P then Q is true when both P and Q are true. Suppose that P is true but Q is false. Then in this case, the rule is broken. So the statement if P then Q is false when P is true but Q is false. Now, suppose that P is false. Notice that in this case, the rule does not require any specific outcome for Q. So, whether Q is true or false, the rule is not being violated. Hence, when P is false, the rule is followed by default. Therefore, the statement if P then Q is true when P is false. To understand why P is the sufficient condition and Q is the necessary condition, assume that the statement if P then Q is true. In the case where P is true, the condition Q is also true. Notice that this is the only case where the statements if P then Q and P are both true. Since if P is true and Q is false, the statement if P then Q is false. This means that the condition that P is true is enough for us to conclude that Q is also true. The words enough and sufficient have the same meaning. This is why we say that P is sufficient for Q. On the other hand, the condition P is true only when Q is true. In other words, for P to be true, condition Q needs to be true. This is why we say that Q is necessary for P. Since the sentence if P then Q is true when P is false and Q is true, we see that the condition P is not necessary for Q and condition Q is not sufficient for P. So, in a conditional sentence, the roles of sufficient condition and necessary condition are not interchangeable. Note that the truth value of a conditional statement is independent of any material cause and effect relationship between the sufficient condition P and the necessary condition Q. Instead, Its truth value depends purely on the combination of truth values of the statements P and Q as described by its truth table. There are several alternative ways of saying if P, then Q. These are frequently used in math, so it is important that you remember them. The most common are P only if Q. P implies Q. P is sufficient for Q. Q if P. Q whenever P. Q is necessary for P. Remember that in the first three statements, the first condition P is the antecedent, and the second condition Q is the consequent. While in the last three statements, the first condition Q is the consequent, and the second condition P is the antecedent. In this set of examples, we are to identify the sufficient condition and the necessary condition in each conditional sentence and give the truth value of the sentence. For the first example, we are given the sentence, if a triangle has three sides, then 1 plus 1 equals 2. The sentence is written in if-then form, so it is clear that the sufficient condition is the statement, a triangle has three sides, and the necessary condition is the statement 1 plus 1 equals 2. Both of these conditions are true. Therefore, the conditional sentence is true. For the second example, we have the sentence 0 divided by 0 equals 1 only if the cosine of 0 equals 1. In this sentence, the two conditions are linked by the phrase only if. Hence, this sentence is the same as if 0 divided by 0 equals 1, then the cosine of 0 equals 1. We see that the sufficient condition is the statement 0 divided by 0 equals 1, and the necessary condition is the statement the cosine of 0 equals 1. The sufficient condition 0 divided by 0 equals 1 is false. Therefore, the given conditional sentence is true. For the third example, we have the sentence 17 squared equals 249 whenever 3 pi is greater than 10. The two conditions are linked by the word whenever. Hence, this sentence is the same as if 3 pi is greater than 10, then 17 squared equals 249. The sufficient condition is the statement 3 pi is greater than 10, and the necessary condition is the statement 17 squared equals 249. The sufficient condition 3 pi over 10 is false. Therefore, the given conditional sentence is true. For the fourth example, we have the sentence, the condition that tangent of pi over 3 is greater than 1 implies that 39 is prime. The two conditions are linked by the word implies. Hence, this sentence is the same as if the tangent of pi over 3 is greater than 1, then 39 is prime. The sufficient condition is the statement the tangent of pi over 3 is greater than 1, and the necessary condition is the statement 39 is prime. It is true that the tangent of pi over 3 is greater than 1, but it is not true that 39 is prime. Therefore, the given conditional statement is false. We now introduce three special conditional sentences that are associated with a given conditional sentence. The converse of the sentence, if P then Q, is the sentence, if Q then P. The contrapositive of the sentence, if P then Q, is the sentence, if not Q, then not P. The inverse of the sentence, if P then Q, is the sentence, if not P, then not Q. Notice that the inverse is the converse of the contrapositive. Remember that the sentence, if P then Q, is not the same as its converse, if Q then P. That is, the roles of the sufficient condition and the necessary condition in a conditional sentence are not interchangeable. For example, let us take P to be the proposition, 0 divided by 0 equals 1, and Q to be the proposition 1 plus 1 equals 2. Since P is false, the proposition if P then Q is true. Since Q is true and P is false, the proposition if Q then P is false. Therefore, the statements if 0 divided by 0 equals 1, then 1 plus 1 equals 2, and if 1 plus 1 equals 2, then 0 divided by 0 equals 1 have different meanings. We now turn to biconditional sentences. Recall that the biconditional sentence P if and only if Q is true exactly when the conditionals if P then Q and if Q then P are both true. As we just learned, the conditional if P then Q is false exactly when P is true and Q is false and is true in all other cases. Likewise, the conditional if Q then P is false exactly when Q is true and P is false and is true in all other cases. So the statement P if and only if Q is true exactly when either both P and Q are true or both P and Q are false. In other words, the statement P if and only if Q is true exactly when P and Q have the same truth value and is false exactly when P and Q have different truth values. There are several alternative ways of saying P if and only if Q. These are used frequently in math, and so it is important that you remember them. Some of the most common ones are P is equivalent to Q, P exactly when Q, P is necessary and sufficient for Q. Notice the use of the phrase exactly when in the second statement, which is also what we have been using when stating definitions. This is because all definitions are, in fact, biconditional statements. For this set of examples, we are to determine the truth value of the given statements. In the first sentence, the statements, a triangle has 3 sides and 1 plus 1 equals 2 are both true. Therefore, the biconditional sentence is true. In the second sentence, the statement 0 divided by 0 equals 1 is false, and the statement cosine of 0 equals 1 is true. Therefore, the biconditional sentence is false. In the third sentence, the statements 17 squared equals 249 and 3 pi is greater than 10 are both false. Therefore, the biconditional sentence is true. In the last sentence, the statement the tangent of pi over 3 is greater than 1 is true, and the statement 39 is prime is false. Therefore, the biconditional statement is false. This is the end of lecture 1.2. Before you proceed to lecture 1.3, be sure to answer the exercises included at the end of these slides. Thank you for your attention.